Hello and good morning, everyone. Welcome to Autodesk Virtual Academy, brought to you by your friends here at KETIV Technologies. I'm Nigel Mbayak, one of the customer success managers here at KETIV, and the person who's been sitting in this chair or that chair for the last 4 years. So, welcome, Nikhil. This is Nikhil Venkat. He's one of the engineers here on our team. Nikhil, how's it going this morning?
Good, Nigel. How are you?
Good, good. Nikhil happens to work on our consulting team here at KETIV. Working mainly with a lot of our automation projects, as well as Nikhil is the in-house expert when it comes to analysis tools, much like Inventor Nastran and CFD like we're going through today. Also, if you didn't know, KETIV is also a partner of ANSYS in addition to Autodesk. So we do provide a lot of different solution types, whether they be from the Autodesk portfolio or the ANSYS one. So if there's anything you need to look at, between those two, let us know, and I'll go ahead and point you to the right direction. Just wanted to start with that because some people are like, wait, I thought you guys were talking about ANSYS a couple weeks ago. What's going on? So I wanted to kind of clear the room, clear the air about what that means. So today we're going to be going over Explicit Dynamics and Inventor Nastran. Nikhil's going to be able to talk to that a lot more intelligently than I will, so I'll let him kind of introduce that. But if you do have any questions, go ahead and type them into the chat panels that you have in your respective viewing tools, whether they be YouTube or live here on Zoom. And let's go ahead and get started. So Nikhil, want to give us a little bit of background on what we're going to go over today?
Absolutely. Thanks, Nigel. So what we're going to be going over today is Explicit Dynamics, as Nigel mentioned. That might seem a little out there. It might seem like it's a little, it's not something that you're working with too often, but in truth, it is what will help you simulate the most real life problems, right? Most real life problems are not static problems. They're not one and done type problems. They have complexities that involve material complexities, geometric, boundary, contact complexities. So this will help us capture all of that behavior, and it'll help us visualize something a lot more realistically, as opposed to the approximations we'll have to make with static problems.
Yep, dynamic meaning it's in motion.
It's in motion. There you go.
Cool. Let's go ahead and get started then.
All right. Thanks, Nigel. So today we'll be talking a little bit about, well, we'll start with dynamics and what it really means. But really, explicit dynamics is connected to nonlinearity, one, dynamics, another one, and then also the nature of the solution, right? So whether it's a time-dependent problem or a time-independent problem. So there's a lot of nuance here. I won't go into all the nuts and bolts of this, but certainly we will touch on all the important ones. And again, if you have any questions, feel free to jump in at any point. The things we'll go over again: nonlinearity, implicit versus explicit dynamics. We'll go over a live demo just so you guys can all visualize what's going on, and then we'll jump into a Q&A session. Let's start with nonlinearity and what that actually means, right? So normally when we think about anything nonlinear, the first thing that comes to mind is plastic. That's really the first thing that we think about when we talk about nonlinearity. But in truth, most engineering problems contain some degree of nonlinear effects. So whether that, as I mentioned, whether that's material-based, whether that's geometry-based, whether that's contact-based, you are likely to see some nonlinear behavior in most realistic problems. As I already mentioned, they can be either time-dependent or time-independent. Now, time-dependent nonlinearity, well, it's exactly what it sounds like, right? It means the behavior actually changes with time. So as you keep, you apply load at a certain rate, at a certain time, and the effect of that load actually changes based on at what point you're measuring the response, right? So whether if you're looking at it, say after 1 second, 2 seconds, 5 seconds, 10 seconds, if the behavior is entirely different, then that is a time-dependent problem. Now, if you were just interested in one instant of these times, or one instant of time, so let's say at 1 second, you want to see exactly what's going on, that can be a time-independent problem. That at that point becomes a static problem. As long as you don't care about the history of the behavior or what that behavior is going to look like after your point of interest, it can just be a static problem. But again, as I mentioned, most problems are not time independent. Most problems are not static. They do tend to be dynamic. They do tend to be time dependent. They do tend to be nonlinear. Now, the question, of course, does arise, well, if you're saying most problems are nonlinear and most problems have all of this complexity, why does it make sense to use linear static problems? Well, the reason is because, one, not all materials or not all designs will hit that nonlinear region to the extent that it's going to affect their behavior too much. And second, and I think most importantly, it's just a much simpler way of looking at the problem. So you know what assumptions you're making going in. Your computation is fairly quick. And then coming out, you can look at the results, keeping in mind those assumptions that you made beforehand. So we'll talk a little bit about the three different types of nonlinearity: material nonlinearity, geometric, and boundary. So with materials, as I mentioned, you think about plastics, you think about materials like rubber. The image that you see down there is a guard, which is made of plastic. It's made of some kind of polymer. And in order to analyze that, you will be using a nonlinear method. Geometric nonlinearity results from problems where you see large displacement, right? So the mighty paperclip you see down there, it started off as a tube of metal. That was then eventually bent into shape, and if you apply enough force, you can deform it and bend it into whatever shape you want, right? And that force, since you can do it by hand, is really not all that high. Now, this is the part where things start to get a little confusing and messy. If it's going to be metal, then the standard assumption is going to be that metals behave linearly, that metals don't necessarily exhibit nonlinear behavior. Well, truth is they do. And metals exhibit linear behavior to a certain point called the yield point. And beyond that, the behavior tends to become nonlinear. So really what we're doing here is tapping into those nonlinear properties of the material itself by playing with the geometry. The only reason that was possible, the only reason you're able to bend it is because it's so thin and so light. So the geometry works with the material properties in order to give you these different types of behavior, different shapes, etc. Boundary nonlinearity, it comes mainly from part interaction, from contacts, right? From here we see the teeth of two gears interacting with each other. This is a fairly complex contact because it's not as if the two teeth are they're fully interacting with each other at all times. As there is motion between one gear and another, the area that is actually in contact constantly changes. And so that level of complexity turns this into a nonlinear problem. Similarly, if you may have heard this before, don't ever try and analyze welds, don't ever try and analyze threads directly in FEA. The reason for that is kind of the same. This is part of the reason for that. When you're talking about threads, again, the nature of contact is not symmetric. The nature of contact is very, very complex between the thread and between the threads. Similarly with welds, you actually have something a lot more complex going on. You've got geometric nonlinearity on the one hand, and then you've also got material nonlinearity because your heat effective zone is not really a homogeneous material. It's a material whose properties you're not quite sure of. So that's another example of boundary nonlinearity as well. Now, how does that relate to the idea of implicit and explicit dynamics? Now, nonlinear and non-static analyses typically require incremental loads, right? The reason for that is, again, you can see that there's so much complexity involved here. And so applying that entire load at once without really considering the time effects or the effects of the, let's say, for instance, you have a force that's being applied on a particular material. That material now switches from its linear material range, linear behavior range, to its nonlinear range. It needs to be able to capture that so that it uses this new behavior, this new nonlinear behavior, for all the subsequent time steps going forward. And so it's important that we use incremental loads and not just one single load applied at one instant of time. Once again, with implicit and explicit dynamics, these loads can either be time dependent or they can be time independent. In any case, though, there is no, you're never looking at a load that is a nonlinear analysis with a load that is time independent, because again, that would be an approximation. Even if you're saying it's going to be time dependent, there is some degree of ramp up that's going to happen with the load. The load will be increased from 0 to full load at some point. And so it's important to capture that as well. Now, the biggest reason, I suppose, these two are different, implicit and explicit dynamics, the biggest reason is the actual mathematical approach that they take, right? So I'm not going to go into the nuts and bolts of that. It's about how you invert matrices and fun stuff like that. So I'm definitely not going to go into that. If you do have questions on that, if you do have questions on the mathematical side of things, then feel free to reach out to us, and we can definitely help you with that. But yes, that is the big difference. The big difference is what the solver does in the background. And that's why, you may have heard of several nonlinear solvers and explicit dynamics solvers. There was an explicit dynamics module or solver in the Algor solver. Some of you that may have used some mechanical, it was called event simulation. That's also what it's called in Fusion 360. It's also called event simulation there. LS Dyna, for example, which is owned by ANSYS, they call it explicit dynamics. And they have an entire LS Dyna, the entire solver is dedicated to explicit dynamics. So it definitely is a big part of simulation. And typically the types of analysis that you'll see from explicit dynamics are crash tests, for instance, right? So you will actually be able to see what the shape of the entire, in this case, truck looks like after it's impacted another object, after it has crashed, right? This is this is the type of analysis they would use in identifying whether or not your vehicle is safe, whether or not, for example, your phone is going to survive a drop test, right? So if you drop it, this is of course a very, 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 very dated image, as you can see, but this is how they verify or validate whether or not the internal circuitry of your smartphone is going to survive, whether your screen is going to survive a fall, etc. Similarly, with other automotive components as well, the actual structural members, what happens to them on impact, etc. Okay. So at this point, I don't want to go through too many slides. So at this point, I will jump straight into the software here. Just give me 1 minute, 1 second while I pull it up. Okay. So what we have here is a chain. It's a 3-link chain. So it's quite simple. And we're actually going to simplify this quite a bit for ourselves from a solve perspective. So first of all, before I continue, this is available in the latest Explicit Dynamics is available in the latest update of Inventor Nastran. So the two new analysis types that you'll see in here are explicit dynamics and explicit quasi-static. We can talk about explicit quasi-static another time. I'd say it's the time-independent version of the explicit dynamics, where that's to put it in a nutshell. But we will go with the dynamics for this one, and you'll notice that you have a dynamic setup in here. You've got damping that you need to define and all of that, right? For this particular problem, what we're going to do is fix one end of the chain, apply a load on the other end of the chain, and see what happens to these areas of interaction, right? Now, I already have some surface contacts defined here. All of them are separation contacts. You'll notice that in the explicit dynamics analysis type, you've only got two types of contacts and not the 6 or 7 that you normally do. Here, we only have separation and bonded. So we're going to specify separation as the contact type between these links. So let's start with, go ahead and remove that. I'll go ahead and make a new idealization here. And for the material, you should actually have, you should have two material libraries in here, the Autodesk material library and the Inventor material library. But if you hit load database, you should in this location, right? See program files, Autodesk Inventor Nastran 2020 or 2019 or whatever you're using, in-cad materials. You should have access to a more advanced material database or a material database for some more advanced materials. If you open that up, you'll see that you have a whole bunch of alloys and silicon and a bunch of other steel grades, etc. So for this one, I'll use carbon steel 1025 hot rolled. Say okay there. And normally, if you were to activate your nonlinear properties, if you were to use nonlinear range on this, then you would go into your nonlinear data and specify what this looks like. But again, we're going to simplify this for ourselves here. So I'll just say okay here. Now I'm assigning the same material to all three links. And so I don't need to associate geometry specifically. I can just hit OK, and this becomes a global setting. Okay, there we go. I'll go ahead and mesh the model. I'll use a mesh size of 0.03. Now, keep in mind that anytime you're running a nonlinear analysis, and I know that this is, we haven't used a nonlinear material, but this is an explicit dynamics analysis. Any kind of nonlinear analysis, make sure you're using linear order elements. This is something that we touched on in one of the previous AVAs that we did. So do you remember which one that was, Nigel?
There was a meshing AVA.
Yeah, there were a couple.
There were a few.
Yeah.
But yeah, so if you're looking to learn more about mesh settings and all of that, we've done a couple of AVAs on mesh settings. So take a look there if you want to learn more about what all these things mean, because it makes a big difference in the solutions that you get based on what you put in.
And how long it takes to run as well.
Absolutely. 14 million elements, Nikhil. Let's do it.
Was that your blue whale?
Maybe.
Okay, so in the settings in here, you can mess with the refinement ratio. You might see different numbers. I may have played with this already, but if you've got, holes and areas of discontinuity in your geometry, then turn on project midside nodes and generate a mesh real quick here. So we don't need this to be super fine. Ideally, you would like to refine the mesh again in these regions of interest, because again, due to the action of the force, we will see highest stress in areas of connection, of linkage. Okay. Now I'll go ahead and add constraints here. So for the constraint, it's going to be very simple. I'll just pick this end, call it fix. And then for the load, I'll choose the opposite end, right? And I want to apply a force in this direction there. So that's going to be in the negative X direction. And so let's use a force of 400 pounds. Let's say 300 pounds. Okay. Now in here, I can specify, or I need to specify how this load is actually going to be applied based with respect to time. So I'll define a new table. Make sure you change this type to load scale factor versus time. We'll call this load ramp up. So times 0, load scale factor is going to be 0. At what is this? 1/10,000th of a second?
It's just 1,000th, I think. Or the 3 zeros?
3 zeros.
Okay.
Yeah. So 1/10,000th of a second, that's when it's going to be fully loaded. And that load will remain through the rest of the problem. Right? So if we're looking at the plot of this, what this actually means is at time equals 0, the load is 0. The load then gradually ramps up until time equals 1/10,000th of a second. And subsequently, the load will remain at the full load, even as the time increases. Okay. So make sure that that table there is selected. You know what, actually, I'm going to reduce the load on this. Get 100 pounds. 300 might be too much. Okay. You say, okay, now there you've got your load. You've got one constraint. That's all we need for the loads and the constraints. We do have the contact set up already. So again, we're just making sure that these surfaces are have separation contacts between each other, which just means that they'll be allowed to separate from each other. That's all. I'm going to turn off damping here. I'm not going to damp the system at all. So turn off structural damping. And under the dynamic setup, we'll change this to duration here. And we'll say each time step is going to be 0.0001 with 25. Okay, let's actually change this around a little bit. So let's switch this over to number of output steps actually. And let's say so go back to duration, time step size.
4 zeros, right?
Yeah, let's say 1 minus 4. 25 output steps. Okay, there we go. That should work. Okay. All right, so we have the whole thing set up in here now. All we need to do is run this. And to run this, we won't just hit run here. You right click on analysis one, say solve in explicit, and say solve.
And then as you would in Inventor Nastran, it runs through all of that stuff that I can't read, and it'll give you a response afterwards.
Yep, exactly. So this can take a couple of minutes. This problem, again, with the amount that we have simplified this, it should be fairly simple.
Yeah,
or it should be fairly quick.
Yeah, if we were actually to do this, we would change a couple of the settings. One being we'd make the mesh finer in those areas between the three links, simply because you're going to see a lot of stress in those areas, and you want accurate results. If there's only like 1 or 2 elements across the body, you're going to get a weird approximation sometimes, but it's based on how it builds it. So.
Okay, so I did mention Fusion 360 and Algor simulation mechanical. So in Fusion 360,
Yeah, we'll just do this while we're waiting for that guy to finish.
while we're waiting for this to finish. So if you actually go into your simulation samples in here, you've got some event simulation samples. And there's some really cool ones, right? Projectile impact's one of them, axe chop's one of them. That's what we're going to be looking at here. So this one's already solved. You can do some really cool simulations, like, for example, seeing what happens when a projectile hits another object, right? So depending on the stiffness of the two materials, this one of them might break, both of them might break. But this is one of those really cool simulations that you can see. Similarly, there's also another one here with the axe chop, right? So this is a number of layers of wood, number of pieces of wood. And as you can see, there's a force being applied on the axe down here. And so as that happens, you can actually see the different layers of wood breaking and splintering and everything. Right. The way you get here, by the way, is go to simulation in Fusion 360. Oh, I'm going to get out of this first.
Okay, you're already there.
Yep. Oh, it's not going to ask me again. But okay, when you do hit simulation,
Generate new study.
yeah, it'll ask you what you want in here. So you may have to do some simplification, but otherwise you use the event simulation, and you can solve this on the cloud.
Yep, and that's in preview mode right now, right?
Mhm.
Yep, so it's not like a full functionality. I think it's full functionality in preview mode. They're just testing it.
Yeah,
They just haven't committed to full release yet.
Yeah,
but
exactly.
They want you to be able to test it and try it out. So they've included it in there. Still chugging away.
Yeah.
Takes a little bit of time. While we're waiting, and I know you showed a little bit of Fusion 360, let's go ahead and answer a couple of questions that came through, though.
Sure.
All right. When you're showing your contacts, you showed the stiffness factor as 0.1. What does that mean? How do you determine, what to use and what kind of implications they are for those things?
Actually, you know what? I actually have one run here. So anyway, we'll talk about that here. So the stiffness factor is a really interesting quantity in here, right? What we're talking about is what is the ratio of stiffness at this region of contact for the two surfaces. So, or for the two, in this case, surfaces. So what we're saying is the contact or the stiffness at this contact region is not going to be the same as the stiffness of the material itself. Since that contact region is so small and there's only so much area there that's being subjected to the contact, that stiffness is actually going to drop. So it's going to be weaker at that area of contact than the rest of the material. Than if you say had just a specimen of material, right? That stiffness factor is specifying that it's now about 10% of the total stiffness, and which is, it might seem like a huge drop, but it really isn't. It's fairly standard for contact like this.
Cool. All right. Do you want to go through some of the solution of this guy right here?
Sure.
And so after you run that in Nastran, you might be able to hear Nikhil's computer chugging away still.
Yeah.
Because it's doing it in the background, but it's not enough where we can't take a look at some of these contour plots. So.
Yes, bear with me. It might be a little slow because it's still running. But okay. So I'm going to make this look a little nicer. So you might see that, oh, there we go. Yes, bear with me for 1 second here, please.
If it just finished the solution in the back.
Yeah, just finished the solution on the other one. So, okay.
I mean, we're not using like a crazy. You don't have to use like insane computers anymore to do any of the simulation. We have just regular like workstation laptops, and that's what Nikhil's working on. And he does a lot of really complex problems on his laptop. So there's this weird stigma where you like need like this crazy machine, but
yeah,
not the case anymore.
Exactly. You know, we're all just using laptops here, and it works perfectly fine. So you'll notice that the results are not in terms of just one final result. They're actually in terms of different instances of time, and that is based on the number of time steps that we set up at the beginning. So of course, what we're interested in is the final time step plot, and you see here that you've got some interference here. That interference may or may not be real. So the reason I say that is because
we're looking at deformation and we're looking at the percentages, not actual.
Right. We're looking at a distorted view of the deformation. So when you actually look at it here, the actual deflection isn't all that much, although you do still see some interference, right? So if I look at this view, for instance, you do still see some interference right here. Now, what do you expect when you see that interference? You expect to see some kind of breaking, some kind of fracture, something of that sort. Unfortunately, we're not seeing that over here like we saw it in Fusion. The reason for that is because we haven't set it up. It's as simple as that. So the way you would set up something like that, if you were to look at results like this and you see there's some interference, is right-click on idealizations here, not on solid one or solids, but on idealizations. And there's something called element deletion. So you add element deletion, you specify which idealization can be deleted and why it would be deleted, right? Is it going to be deleting based on negative volume? So is it going to be breaking? Is it going to be based on the strain? Is it going to be because of thinning, effective strain, etc.? Right? And you say okay, and then again, this is going to increase complexity and increase computational time. But if you want to see a more accurate set of results, then yes, absolutely, you can turn it on.
Yep, and then that was like element specific, which brings it back to your mesh.
Your mesh, exactly.
If your mesh isn't fine enough, it's going to get rid of these huge elements, and it's going to look super funky.
Yep.
So the more refined your mesh is at those areas of interest, right, where those high points of stress are, the more accurate your model is going to look like if it starts removing elements. Because you're going to get some like weird jagged edges and stuff. It's like, why did it remove this whole element?
Exactly. Now, as I mentioned, the solution is in terms of time steps. Another area of interest might be at what point in time does the behavior actually change? At what point does it start behaving the way we're seeing it behave at the end? So what you can do is actually set up an XY plot here. So on the left, under analysis 1, it's just below results. You can double click on XY plot, and over here, under the X-axis output sets, you can choose multi-set. If you're going to do single set, then it's going to plot the results at one particular time step. If you're going to do multi-set, then you're looking at it from one time step to another, right? So here we're going from start to finish. And what we're looking at is the displacement, right? So you can add that curve here. You can say show XY plot. And you can see here that the displacement increases gradually to a certain point and then starts to behave slightly differently. What this also looks like, if you're a materials person at all, remarkably, is this looks like the stress strain curve of any metal, of let's say steel, right? This looks almost exactly like the stress strain curve of steel. So this problem kind of gives us a good idea as to how that transition between linear behavior, which is what this is, and nonlinear behavior happens, right? Anywhere where you see a straight line between displacement and, or between force and displacement tends to be linear behavior, and anything that is not a straight line tends to be nonlinear. So this is a great example of that. And of course, similarly, if you want to look at the stresses, you'll have to switch this over to elemental stresses, to an elemental plot. So let's say you want to look at the solid 1 MESI stress, multi-set, add, show that plot. Element 1. Oh, so we're only looking at it for one particular element. So yeah, it's that particular element doesn't necessarily have a stress through the time, but the total displacement does change.
Yeah, because you selected element ID 1.
Yeah. So you'll have to select a group of elements, and
yeah, the element 1 is probably like somewhere in space somewhere.
yeah, yeah. So what you'll need to do, just so you know, to if you want to get a group of elements, right under results, right under analysis 1, you have this drop down, or this collapsed model space. So you scroll down here, you've got something called groups. So you can make a new element group or a new node group, and then you can select all the different elements that you want in here. And then when you plot the result, you're plotting that particular group.
Yep. Awesome. Cool, Nikhil. Hopefully people learned a lot. I know we had to simplify the problems. That's solely for time, right? A lot of these things are very complicated. And I would suggest you do the same when you're starting your simulation process. I would simplify your setup as much as possible so that you can get a quick result and see if you're going in the right direction.
Exactly.
Oftentimes we see people try to make it as realistic as possible. In regards to their setup, it takes like 15 hours to run the simulation, and then their idealizations were wrong.
Yeah, exactly.
And so they have to do it again. So I would, and I think Nikhil would say the same thing, is I would simplify the process as much as possible, and then slowly complexify everything, right? Add elements in those areas. Just see if you're getting what you think should happen, right? Based on pulling that chain, you would understand, okay, the stress is going to be here, all of that stuff. Well, slowly, during that whole process, you're going to add things to there. So I wouldn't add the element removal like on the front end, right? I would run it as you might want to run a modal problem first with the whole thing. Make sure that your loads and your constraints are correct, and then slowly ramp up into adding elements in those areas and deleting the elements and things like that.
And even something like just maybe simplified, maybe just focus, change your CAD a little bit to focus only on that region that you're interested in, and then reapply the forces there.
Yeah. Yep. All right, let's jump into questions. If you have any, go ahead and type them in, and we'll go ahead and address those. Grant's asking, when you choose the time steps, how do you determine those numbers, and how do they affect the results? Well, the easy part is the number of time steps. The more time steps you have, the longer it's going to take you to get the result.
Yep. Essentially,
you're getting results at time equals, well, most of the time.
Yeah, most of the time, yes. But again, it also depends on the type of the problem, right? If you don't break it up enough, then it's going to just keep spinning its wheels trying to solve that one single time step.
Yep.
Whereas if you do break it up, sometimes there is a chance that you've broken it down too much.
Yep.
And so it just takes too long to solve everyone. So there is a balance that you need to strike.
Absolutely. You don't want 1 or 2 time steps for, I won't even say that. You don't want too few and you don't want too many. Because if you have too many and they're all so similar to each other, well, it's going to compute that infinite times or however many times you put it in there, and it's going to suck. If you have enough, like Nikhil said, you're not going to have enough information to look at the results and kind of determine what happened with that problem in the first place. What do you do for cases where the force changes based on the position?
You mean follower forces?
So he has 2 examples here, I guess. One where fixed objects are connected by a spring, so the force on the endpoints depends on the position of the...
Well, you would use a rigid connector then, a rigid spring connector then at that point to actually simulate what that spring force looks like and what that energy absorption looks like over there. So yeah, I mean, that's something we can definitely explore. It might require some creativity, but yes.
Yep, and then electromagnetic forces. I wouldn't use Nastran for that.
Yeah, electromagnetics, Nastran's not, unfortunately, doesn't work with electromagnetics.
But we do have software that does.
We used to.
Team. On Jim's team.
On Jim's team, yes. So Autodesk used to have simulation mechanical, so I don't know if that's where the question's coming from. But Nastran doesn't have that. But yes, we definitely have solutions here at KETIV that can.
Yep. Yeah, that would just be outside of the
electromagnetics.
Autodesk portfolio and into the ANSYS portfolio, which we also support.
Yeah.
This is Autodesk Virtual Academy, so we can get to that later. But sometimes you have ANSYS stuff on here as well.
Well, today it's Autodesk Virtual Academy. It
That's
might be
true.
ANSYS Virtual Academy another
Next
day,
week.
you know?
Yeah, absolutely. So if you have any follow-up questions on that, definitely reach out to us, and we'll have someone like Nikhil or someone on one of his counterparts on the ANSYS team talk too as well, depending on what you're trying to complete. Is there literature for explicit simulation in Nastran?
Well, not yet. There are tutorials.
There's
one or two.
I don't think there's any books on Inventor Nastran yet for Explicit Dynamics.
Not yet. No, I mean, Autodesk is still, this came out in the most recent update, came out a month or two ago. So they're still working on kind of getting that documentation together, and you know, this will definitely be a big part of the 2021 release. Now, I do know that there is some interest in-house here as well. So a couple of our other engineers, they've been looking into Explicit Dynamics, and they have some ideas as to what they might be looking to use it for. So you might see a couple of these Explicit Dynamics AVAs come down the road as well. So definitely keep an eye on this. But yeah, we will let you know as well if
I don't think there's any textbooks or anything, but there is some stuff, and I believe might be some stuff in the help documentation. Maybe at least for regular Inventor Nastran stuff there is. For the Explicit Dynamics stuff, I don't know if they've added to the help docs yet.
I don't think they have yet.
Yeah. I would look at the knowledge base too. So knowledge.autodesk.com has a ton of information on it. And that's where I would start. If it's going to be somewhere, it's going to be there.
Yeah.
All right. Another question. Do you have training on simulation tools do you have training on fully simulation tools? So I think, Enrico, I think your question is like, do we train people on Nastran? So yeah, Nikhil's one of our instructors for Nastran. And so whether that be Nastran in-cad, if you're previous to 2020, or Inventor Nastran after 2020. Yeah, we do have a full curriculum for training. A lot of times we can tailor the training based on what your organization needs, right? Not everyone needs every simulation type in Nastran. I guarantee you there are very few companies out there that need everything that's in there. You're probably going to need 3 or 4 of the modules based on what you manufacture or build. So let us know if that's something you're interested in doing. We do offer training for that as well. Just reach out to myself or Nikhil, and we'll be able to pass you over to the right people to get that taken care of for you. Cool. I'll leave it open for another 30 seconds or so for anyone to ask any more questions that you do have. And in the meantime, I'm going to go ahead and make a couple of announcements for AVAs. So for AVAs, next week, we've got my good friend Jose, who sits in the same section of the office as we do. He's going to go over some of the key things to implement Vault Basic. And so Vault Basic is something that's included with the Product Design and Manufacturing Collection. It's a data management tool if you don't know what it does already. And it's also CAD aware, which I think is really key there, whereas say folder structure in your computer is not. So he'll be going over some things to look out for when implementing Vault Basic. I know that's something that a lot of people don't want to do because there's a perception that it's super complicated. Not really. And so we're going to kind of demystify that for you guys.
Basic.
Absolutely. There's not a lot of stuff to set up. When you get into Vault Pro, maybe so.
Yeah.
But in Vault Basic, it's so easy. Just set it up.
Hit a few buttons and
absolutely.
Run through it.
And then in 2 weeks' time, Adam Evangelista is going to come back and do something related to this.
Yes.
And that's going to be nonlinear analysis on orthographic materials. I still haven't put my head around that. Nikhil, can you give us like a little blurb about what that actually means?
Sure. So most materials that we talk about are isotropic materials. They're called isotropic because their properties, if you measure them across different directions, their properties will be exactly the same. Orthotropic materials, the properties differ from each other in orthographic directions. So every 90 degrees, the properties are going to change. Now, there's also anisotropic, where the properties are entirely directional. So it's totally random depending on which direction you measure the properties in.
Yep.
The properties will be entirely different. But orthotropic still does have some kind of pattern to it. So the 90 degrees, the X, Y, Z directions are where the properties will differ.
Yep.
So wood is a great example.
Yep.
You know, wood, you've got long fibers, and then the strength along the length of the wood is very different than the strength
across the wood.
across.
Yeah. If you've ever, if you've taken a materials class in school, you have to draw cubes with all those dots on them. This is where that comes in. So that's all I remember. So yeah, definitely stay tuned for that. That's happening in 2 weeks. Adam is going to use some real world problems, and
Yep.
I love when Adam comes up with AVAs, strictly because Adam always comes up with an AVA that has to do something with a real life problem that he has.
Yep.
One of them was like, how hot does my coffee stay? Can I make it stay hot? And this one, like, he was building IKEA furniture. He's like, is this stronger in this direction or this direction? So, well, that's like particle board, so I guess it's isotropic. So
It is
absolutely. So definitely stay tuned for that in 2 weeks, but we'll look forward to that one as well. So again, thank you everybody for joining us today. Like I said, if you have any questions further about Inventor Nastran in-cad, Inventor simulation, simulation mechanical, fusion simulation, ANSYS simulation, send them over. We'll go ahead and help you take care of it. We send a lot of emails, so just reply to one of those.
Yeah, absolutely. Oh, and one more thing, which I may or may not have mentioned, the Fusion 360 simulation that we saw earlier, all of that is with the Nastran solver. So Fusion does have the Nastran solver, and that's what we were using.
Absolutely. Cool. So again, thanks everybody for joining us this week. We will see you next time. Bye-bye.
Thank you.